Let's state the second duality test one more time, and then we're going to give some examples. The second duality test says that suppose the second partial dualities of the function f are continuous on a disk with center a, b, and suppose that the partial duality with respect to x and with respect to y both are equal to 0 at a, b, then D, which is this symbolic determinant of this matrix, these two cases is for D is greater than 0. The last case here is for D is less than 0 at less than 0 at a, b. If D is greater than 0, we have two cases. If fxx here at a, b is positive, or when it's negative, that is case B. Okay. Let's try to kind of relate to the second duality test for 110A. This one kind of played a role like the second duality. So if this second order partial duality with respect to x and x again, if it's positive, kind of think like the concave of things, then the function value will be a no-cone minimum. And if that is positive, kind of think about like it's like a concave down graph. Okay, and the function value will be a no-cone maximum. Okay, so it's helpful if you can relate this to calculus 1, the second duality test, and that will make things a little bit easier to remember. All right, so that's how I remember this too. Okay, if the D here if this one over here is less than 0, then what happened here is the function value is not a no-cone maximum nor a minimum. Okay, and the situation here is a, b is going to be a saddle point. So neither, and that is a saddle point, just like what you see in the picture. Now we're going to find no-cone max and no-cone mean, and also saddle point of this function. So to do that, we first locate critical points. Okay, how do we find critical point? We'll take partial duality, and then we set them equal to 0, right? Okay, so what's the partial duality with respect to x, everyone? Okay, 4xq minus 4y, good. Partial duality with respect to y, 4yq, and then minus 4x, okay, good job, okay. Now, after this, we're going to set the partial duality equal to 0, right? We're going to set this equal to 0, and we're going to set this equal to 0 in order to find critical. We're going to set this and this equal to 0 in order to find critical point, right? Okay. For this equal to, okay, let's write down the equation. For this equal to 0, we can divide by 4, and we'll get xq minus y equal to 0. For this equal to 0, we can divide by 4, and we get yq minus x equal to 0. Now we're going to solve this system of two equations. And the way that we can solve this, we can use substitution method, right? Okay, so we can substitute. From this one, we get y equal to xq. And when we put y equal to xq in here, then we'll have, what do we have? Xq and q, that's x to the 9, and then minus x equal to 0. Now we take out the greatest common factor, which is x, and then we get x to the 8, subtract 1 here. From here, we can tell what does x equal to. X, yeah, so x will be equal to 0, or x equal to, so I heard Eller say 1, but that's one more, also negative 1, plus or minus 1, right? So when you take the 8th root of 1, you get 2 root. This is an even root. So you get plus or minus 1. Okay, good. All right, so there are 3 real roots, right? 0 and plus or minus 1. So we should have 3 critical points, right? Okay. So the 3 corresponding critical point will be this, this, and this. X is 0, 1, -1 into this, y equal to x cubed to find the corresponding y value, right? Okay, so those are the critical points. So we found those critical points. Now, let's try to use the second derivative test. Okay, second partial. Then we had to take the second partial derivative. Okay. So for your convenience, I put this first partial derivative here, so you can take second partial derivative. Okay. Take the second order partial derivative with respect to x again. What do we get here? Differentiate this with respect to x, we get 12x squared. Okay, good. Okay, what about take the partial derivative this with respect to y, we get -4, yes. Okay. Okay, fyy, okay. So take the partial derivative this with respect to y, that will be 12 y squared. Yes, you got it, good job. Now, after this, remember we're going to compute the d, right? So we're going to compute the d over here. How is d defined here? This is fxx, fxy, fyx, fyy, right? Okay, the determinant of this. Okay. Now, so that will be fxx times fyy subtract fxy squared. Okay, can you guys do the calculation? Oh, actually, we can just put it here, okay? So you will substitute all this into here. Then we end up with this. So we end up with this. Now, to use the second derivative test, we're going to test the d here at all those critical points, right? Let's test the d here at the first critical point. Okay, so the critical point here is 0, 0. Substitute 0 and 0 in here. That is equal to -16, right? So that is negative. So it follows from which case? Which case is this? When d is less than 0. Case A, B, or C? C. Yeah, you said C. You got it. From case C, then at 0, 0, the origin is what kind of point? Is saddle, right? When D, let's go back, okay? Right here, this one, okay, look at this one. When D is less than 0, then that point is a saddle point, okay? Okay. This two case is what D greater than 0. The saddle point is when D is less than 0. So case C, we have a saddle point, okay? So that is a saddle, okay? So the function has neither local max or mean at 0, 0. Okay, so that was the first critical point, right? So the first critical point is 0, 0. The second critical point is 1. 1, 1 is the second critical point, right? 1, 1. The last one is 1, -1. Okay. So substitute 1, 1 over here, we get 128, which is positive. Okay. And also substitute that into fxx. Okay. Here's fxx. When x equal to 1, that's equal to 12, which is also positive. D is positive, fxx is positive. Which case is that? Case 1? Yeah. Someone just put that one finger. 1. I don't want to talk. Okay, just 1. Okay. Okay. So from case A, the first case, the function value at that point is a local one. I see you guys. I roll up. Remember that. Think about the second derivative test. So when fxx here is positive, it's kind of like concave up, right? So that point has to be a local minimum. Yes, local minimum. We got it. Okay. And similarly, the last critical point is -1, -1. Okay. And it is the d is greater than 0 and f(x) is also greater than 0. So the function value at -1, -1 is a local what? Both d and this is going to be positive, then it is the first case, right? So it's a local minimum. Yeah, remember this kind of like the second derivative. Okay, so kind of like think about it concave up like that. So if it's if it's concave, it's like concave up like this. Okay, then this has to be this local minimum, right? Okay, all right. So that's a local minimum. Okay. Wow, that's a lot of work, but it's actually it's doable. Okay, it just need to be persistent. So we actually graph the function here in 3D. This is the graph of the function. At 0, 0 here, it is a saddle. At 1, 1 here is a local minimum, the function value. At -1, -1, the function value is also a local minimum. So that's how it looks. Now we continue example 4. We're trying to find and classify the critical point of this function. All this function here, this is a polynomial function. Okay, so the domain will be all R2. We're trying to also find the highest point on the graph of the function. So to do this kind of problem, we always need to find critical points, right? And to find critical point, we need partial derivative. So let's take partial derivative first. So you guys are expert in taking partial derivative already. Can you guys tell me what is partial derivative of the function with respect to x? So we're going to take the derivative. So we're going to focus on the x. So this has an x train, this has an x train, and x train. And we just take the derivative of all those trains that contain x with respect to x. Okay. So partial derivative this with respect to x here will be what? 20 xy, yes, 20 xy. And then differentiate this as negative 10x. Okay, good. And then derivative this with respect to x here is negative 4x cubed. Okay, so got this. Okay, now similarly, you can find partial derivative of this with respect to y. This time you're going to focus on the y. This one has y train. And you take derivative of all those trains with respect to y. We should get 10x squared minus 8y minus 8y cubed. Okay, so those are the partial derivative of the function. This with respect to x, this with respect to y. Now to find critical point, we just set partial derivative equal 0. So we're going to set this one and this one equal 0. Let's label this equation 4, equation 5 here. And then we're going to solve this system of two equations. That might be a little bit tedious to do it, but we can do it, okay? I think the part here is all those algebra might be a little bit tedious, okay? From the first equation, we actually take out the greatest common factor, which is 2x. Now, for this equal to 0, we'll have 2x equal to 0, which is when x equal to what? When x equal to 0, right? Or this second vector over here, this vector over here equal to 0, okay? By the 0 vector property. So now let's think about case by case. This. Now, in the case that x equal to 0, so let's think about if x equal to 0, and we're going to put x to be 0 in this equation, and what we're going to end up with is negative 4y minus for yq is equal to 0. And you can take out this common factor negative 4y. You get this equal to 0. For this equal to 0, can 1 plus y squared equal to 0? Can that be equal to 0? Never, right? It's always greater than equal to 1. So the only possibility is the y here equal to 0. So from this, we will have y equal to 0. So if x equal to 0, then y has to be equal to 0. So we have the critical point that has x to be 0, y to be 0. Okay, so that's one of it. So that's the first case, okay? From this equation over here, we have the case x equals 0 or this factor here equals 0. So x equals 0, we get y also equals 0, so we get that. Now let's consider the case, this one. When 10y minus 5 minus 4x squared equal to 0. And now we can actually isolate x squared. So x squared is 5y minus 2.5. All right. And putting this, I'm going to put this, okay? So we're going to put this one into equation 5. So put it over here. Because this one here comes from equation 4. Now we're going to put this into equation 5, into the other equation. And substitute x squared here by 5y minus 2.5. And you end up with this equation. And you have to solve this cubic equation. It is a little bit challenging, okay? There's a formula for cubic equation, but that's very complicated. Just like quadratic formula, they have formula, but it's too complicated, so complicated, okay? So one way to do that is to use a graphing calculator or computer graphing device, okay, or some app, okay, to graph it. So graph this one over here. Actually, graph this function, okay? Graph this function over here. The graph look like this, and you set the equal to 0. So that means the y coordinate equals 0. So we get this intercept over here. Okay, this intercept, this intercept, this intercept. And using the feature in, you can zoom in or trace, and then you can get those y value here. So this is y1, this is y2, and this is y3. You got that. So my comment to solve this kind of system 2 equation here, a lot of time you can actually try to solve it by graphing. So you can try to graph this and and then try to graph this and look at the intersection. Okay, so that's one way to do it. And then by doing that, you get those y. Okay, you get those y right there, and you can go back to 5x. How do you go back to 5x? Use this. X is positive and negative square root of this. Okay, x squared equal to that, so x is plus or minus square root of this. So this is what we have over here. And substituting the corresponding y there, you get the corresponding x value, and here's the table. Okay, so you found those critical points. Okay, this one, this one, this one, by doing this. Now, if you're looking at the graph right there, you can see that those correspond to this 5 point right here. Okay, 2 green dot right here and 3 pink dot here. Each dot over here correspond to a critical point. Okay, and you can see here and here, those are the saddle, right? And then this and this looks like a local one. The function value will be local maximum. Yeah, you got it. Yeah, this one here, saddle. Yeah, okay. So green are the saddle and the pink the function value local maximum. Okay. This problem is a little bit tedious, especially solving the system 2 equation in x and y. Okay. At that time, you can try to use some graphing device to graph it. Okay. So there are lots of those apps you can use. Okay, the next example, we're trying to find the shorter distance from this point to this point. Let's have a mental picture of what that means. So this is the plane over here. So I just draw a plane over here. And then this is the point, right? This is a point over here. The shorter distance from a point to the plane will be the distance will be you draw a perpendicular line to the plane. The distance from here to here is the shorter distance, right? Now, if I label this point on this plane over here, x, y, z, so let's label this point here x, y, z, then what's the distance between these 2 points? What's the formula? Distance equal to square root of what? In this case, will be what? X minus, what's the distance formula? Do you guys remember the distance formula, right? So the distance formula is what? Distance equal to square root of x2 minus x1 square plus what? y2 minus y1 square plus what? z2 minus z1 square, right? So that was the distance formula. So given you 2 points. So now we have 2 points, right? So the distance here will be square root of x minus 1 square plus y minus 0 square plus z plus 2 square, right? Okay. So that's the distance. And what are we trying to do? We're trying to find the minimum of this because you try to find the shorter distance, right? Now this is, this one has 3 variables, x, y, z. We can actually eliminate one of the variables, let's say z right here, because x, y, z satisfy this equation. So we can, from here, we know that what the z here equal to, right? So z is equal to 4 minus x minus 2y. And then we can replace the z over here by this expression in x and y. So then we'll have the distance in terms of x and y only. Okay. Then we have this one over here. Okay. Now why? Because we know how to use those second derivative tests, etc., to find the extreme value for function of 2 variables. But this one has 3 variables. We're not able to do it. So we want to eliminate one of the variables, the z here. So then it becomes a function of 2 variables, x and y only. Okay? Now we want to minimize this. However, the square root make it a little bit complicated. So we think, how about we just take away the square root? How about I just square the distance? So if I square the distance, I don't have the square root sign. But if the distance is minimized, then so is the square of that. If the square of the distance is minimized, so is the distance, right? Okay, so we're going to minimize d squared instead of just d, because they're equivalent. The result will be equivalent if you try to minimize d squared or d. Okay. Now we try to minimize this, so we need to find those critical points. To find critical point, we need to set the partial derivative equal to 0. So we go ahead and take partial derivative and set that equal to 0. Okay, everyone tell me what's the partial derivative of this with respect to x. Let's focus on the term that has x over here. What's the derivative of this with respect to x? You just said that is by the chain rule, right? So it is going to be what? 2 times x minus 1, right? Okay, and then here, for this part here is what? 2 times this, right? Okay. Now, when you take partial derivative, you use the chain rule. The derivative negative x is negative 1, so that's why here is there's a minus sign here. Okay, so we got this one over here. Okay, how about we take a partial derivative with respect to y? Okay, this time we focus on the y. So focus on the y here, and also this one. What's the partial derivative of this with respect to y? You said 2y? Yeah, got it. 2y minus 4 times this. Okay. because the derivative of -2y with respect to y is -2. -2 times, and then you also have this 2 parenthesis to the first power. So this is a -4 here. Okay. Now we're going to set this equal to 0. So we're going to set both of them equal to 0. The book actually, so you're going to multiply this in, distribute, and combine item. You end up with this. You set both partial derivative equal to 0. Now you just need to solve the system of two equation. So a side note over here for you guys to solve the system of two equation, you can actually solve by graphing. Okay, so you can graph both this equation and this equation and look at the intersection. Why do they intersect? Okay, if that's more helpful to you guys. This one is actually not that hard to solve. Okay, you can actually solve by the addition method, right? Okay, you can subtract the two equation. Now, when you solve this system of two equation, you get x to be 11 over 6 and then 5 over 3. Okay, trust me, this is right. Okay. Now, we found this critical point, but what else do we need? We need to look at the D, right? We need to look at the D because to see what happened. So in order to look at the D, we need the second order partial derivative. So we take fxx. Okay, take the derivative of this with respect to x again. What do you get? 4. Yes, you got it. Okay, 4. And then fxy. Is it 4 again? Yes. Okay, fyy. 10. Yeah, 10. Yeah, so that will be 10. And then you calculate d over here. Okay. So you calculate the d using this, and that's positive. And fxx is positive. Okay. So when fxx is positive, think about it's kind of like the concave up case. Okay. This one here, think about like the concave up case. So what kind of what happened at that critical point? We have a local what? Minimum. Yes, local minimum there. At that, okay. Intuitively, we can see that this local minimum is actually an absolute minimum. Why? Because this local minimum is also absolute minimum because there's only one minimum. There's only one shorter distance, right? There's no other, right? So yeah, so that is also the absolute minimum, okay? Because there must be a point on the plane that gives you the closest, the shortest distance from this one to the plane, okay? So that is also the absolute minimum, okay? How do we find the absolute minimum? You can just go ahead and substitute the x and y value into this expression to find that. So x is 11 over 6, subtracting 1. So that is what? 5 over 6, right? And then y is 5 over 3. So put here. So that's 5 over 3. And then for this one, to do the calculation, that's 5 over 6. So the result is 5 over 6 times square root of 6. And that's a shorter distance from this point to the plane that was specified. Question about this? Wow, that's a lot to do. Okay. Let's look at example 6. Example 6 is so similar to what we have did in Math 110. 110A in 110A. At that time, we do the optimization problem, right? So we're trying to make a rectangular box like this without a lid. So it's open top. There's no top. And from 12 square meter of cardboard. At that time, this problem, actually, you can do that without using 110C. You can just use Math 110A, okay? Now, let's see how we do it in 110. How do we approach this problem in Math 110C, in Calculus 3? So the value of the box, okay, first we're going to define the variables. Okay, so x is the length, y is the width, and the z to be the height. Okay, so define the variable first. So like that. So the value of the box is equal to what? X, Y, Z. Okay. Now we're trying to find the maximum of this value here, right? So, but this is a function of 3 variable, but we want it to be a function of 2 variable only, so that we can use the theme that we just learned, right? So we need to eliminate one of the variable, so that it becomes function of 2 variable only. What information we can use to eliminate one of the variable? The area of the box, right, is going to be 12 square meter. Okay, this one has open top, right? So the area here will have this front and the back and the side, left side, right side, and the bottom, but no top. Okay. So what's the area over here? Can someone tell me? Okay, just think about this area here. What's the area here? X times Z. How many of this? You got 2 of this. Okay, so you got 2 of this. Okay, and the front and the back. The front here, Y times Z, and you have 2 of that. So 2YZ. Now we get to the bottom. For the bottom is what? It is X times Y. And we only have 1 of this, right? Because there's no top. Okay, that's equal to 12. Now from this, we're able to solve for Z. Okay, Z is equal to this. And then we can replace this. So we can go ahead and take this. Put this one over here and put it over here. Okay, then V here will become a function of 2 variables, X and Y only. Okay. Oh, it looks kind of complicated. Okay, let's see how do we. So someone said, wouldn't it be easier using the calculus 1 method? Maybe, yeah, maybe. You can try it at home, okay? Okay, but let's see how this one goes here. Now, for this, we need to find critical points. So we take partial derivative of this with respect to x, take partial derivative of this with respect to y. Okay, you can verify is this correct or not, but okay, it is correct. Okay, and we're going to set the partial derivative equal to what? Equal to, how do you find critical point? Set partial derivative equal to 0. Okay, so we're going to set that equal to 0. Now set this one equal to 0. The only way that this equal to 0 is the numerator on top equal to 0, right? Okay, so you're going to focus on the numerator on top. This one, right? And you're going to focus this equal to 0. Okay. That's the only way you can get 0. Okay. When the numerator equals 0, right? Okay. Now, for this equal to 0, well, if y equal to 0 and x equal to 0, let's think about the case x and y equal to 0. If x and y equal to 0, what kind of case you have? If x and y equal to 0, do we have a box? We don't have a box. There's no value for that, right? So that one doesn't make sense, right? So that cannot be 0. This, okay. So we cannot have x or y equal to 0. So the only possibility is what? It's going to be this equal to 0 or this equal to 0. That's the only way. Because x and y cannot be equal to 0. Otherwise, we don't get a box, okay? So we're going to solve the 2 equation, which is this one and also this one. Set that equal to 0. And when we do this, looking at these 2 equations over here, okay, they look so similar, right? So can we subtract the 2 equations? So if I take this equation, subtract this equation, looks like this, and this one cancel out, right? And giving you what? Okay, let me label this equation then. This is equation A, this is equation B. If I use B subtracting A, then we're going to get this equation, right? Okay. So we're going to get x squared minus y squared equal to 0. So x squared equal to y squared. So therefore x equal to y. Why? How come it's not plus or minus y? Because x, y, and z, those are the dimensions for the box, right? Can they be negative? Yeah, cannot. So x and y has to be positive. So x equal to 1. And then now you go back and put x equal to y into this equation. You get this. And you put it in this equation, you also get this. From here, can you tell me what does x equal to? Solving this equation. Looks like x squared should be equal to 4, right? So x equal to what? 2. Yeah, it has to be positive. So positive 2. And x equal to 2, then y will be also equal to 2 because x equal to 1. And then now you can put x and y back and to figure out the z. Okay, z is equal to 1. After all this work, you see that critical point is 2, 2. How do we know that? When x equal to 2, y equal to 2, and z equal to 1, that gives you the maximum value of the box. We could use the second derivative test to show that. However, we could just argue from the physical nature of this problem that there must be an absolute maximum value which has to occur at this critical point when x equal to 2, y equal to 2.